Welcome to Lecture 16, the last lecture for our programming language course, Scheme Interpreter Design. Chapter 10C, Scheme Interpreter Design. Objective: we will introduce a subset of scheme language for the interpreter design, and then design the repeat loop for it. And it is an integration of scheme interpreter. We will have three different languages: a very simple calculator language, and then Lisp language, and then Lisp language. Okay, three versions, and basically it's from very basic set to complete set to more advanced set, three different sets. So in this course, we first introduce the idea of the programming language. And in the programming language course, basically, first thing you need to learn is how to design a language. So when we develop a programming language, first thing you need to do is design a programming language. Okay. And in order to design a good language, you must know about your programming paradigm. That could be imperative programming or object-oriented programming, or functional programming, or others such as neural network or anything else. So design the language and find the programming paradigm as the second thing you need to do, which paradigm you use. Then we go into the next level that actually is the leg and yet, okay, leg and yet. The lexical analyzer design and parser design. Finally, you put into the whole interpreter or compiler. So this very last lecture, we are focused on putting things together for the interpreter and compiler. In lecture 15, we focus on a single expression interpretation. But now we need to add more, because this one does not including the loop, does not including the function code, does not have the environment. So here we are going to discuss a few issues regarding the compiler or interpreter with the environment or the loop or the function. So that's why here we need to add more component into our interpreter. And basically they are environment issue. So basically in your design, you may have parser issue, you may have lexical analyzer issue, and you may also have the environment issue, and you need to take into the account when you implement a language. Overview. How to write a Lisp interpreter. Lisp is a older name for the scheme language. It was originally a Lisp language. The lecture has two purposes: to describe how to implement computer interpreter in general, and in particular to build an interpreter for the most of the scheme dialect or Lisp. So Lisp is older language, and now it called scheme, and recently it was renamed to Recursion. So Lisp, scheme, or Recursion is the same language, and using Python 3 as the implementation language. And Python, we know that it's not the most efficient one, so it basically is a way we do prototyping. I call my language and the interpreter Lisp. And years ago, the author showed how to write the semi-practical scheme in Java and the common Lisp. So the same author also developed a different language, the interpreter for different languages, in different languages. This time around, the goal is to demonstrate as concisely, as simply as possible. Okay, so basically try to make the design simple. So syntax and semantics of scheme program. The syntax of the language is the arrangement of character to form correct statement and the expression. The semantics is the meaning of the little statement or expression. For example, the language of mathematical expression The syntax for adding 1 plus 2 is 1 plus 2, and the semantic of the application of the addition operation to the two number will yield 3. We say we are evaluating the expression when we determine the value. We say that 1 plus 2 evaluates to 3, and the right 1 plus 2 produce 3, okay? So here we have a comparison between the syntax and semantics of scheme program. So left-hand side is Java language. You have if and then Boolean expression. X value greater than 0, we return the function of AI plus 3 times I, comma, and create a new array of strings, okay? And in scheme, you actually can do the similar thing and create a function, okay? So Java has a variety of syntax convention, but scheme syntax is much simpler. Scheme program consists only solely on expression, or we call it list. There's no statement and expression distinction. So statement and expression is the same. Everything is list. Number and symbol are called atomic expression because they have the value. They can be broken in two pieces because they are called atomic. So they are not expressions, so you cannot further expand it. These are similar to those Java counterpart, except that in scheme, operators such as plus, greater than are simple too, and they are also considered to be function. And we treat these the same way as a and the function, okay? So they are symbols. Everything else is this expression, so parenthesis is followed by another parenthesis and put this item inside there. This starting with a keyword if is a special form. The meaning depends on the keyword. So, but you can also consider that actually it's a function. This starting with a non-keyword such as fn is a function called a function. So the beauty of scheme is that the full language only need 5 keywords and 8 syntactic forms. So 8 different list patterns and 5 keywords. And Python has 33 keywords and 110 in syntactic form. And Java has 50 keywords and 133 syntactic form. And more complicated keyword set and syntax form, then your language will be bigger and compiler will be harder to write. All those parentheses may seem intimidating, but scheme syntax has the virtues of simplicity. So scheme is very simple and consistent. In this lecture, we will cover all the important points of the scheme language and its interpretation. But we will take 2 steps to get there. So we will define a simple language and a full language. And finally, we will have the extra step, the 3rd step, to study the advanced version of the scheme language. So now let's look at language 1, Lisp calculator. So this one is a limited Lisp language only for calculator. So Lisp calculator is a subset of scheme using 5 syntactic forms, 2 atomic, 2 special forms, and a procedure code, 5 different forms. And this P calculator lets you do any computation that you can do on a typical calculator. And as long as you are comfortable with the prefix notation. So it's a prefix notation, not infix notation. And you can do 2 things that are not offered in typical calculator. That is if statement, okay? You can do that. So you can actually here, you can do divide R 10 and then times pi and then times R. So pi R, this one will calculate pi R squared for you. So there are available reference syntax that actually is simple. Constant literal, we call it number, okay, in terms of Lisp language terminology. So simple is actually a available reference or ID or ID. Number is constant, and if test consequence and alternate. This one is a Boolean condition in here, if true, you return this value. If false, you return this value. It's a conditional list. And we have the define, and then define will actually set the symbol to be the same as the expression. It can define a variable or define a function. Okay, procedure code, you put the procedure function name and then parameter over here, and you can evaluate the function. So these are the 5 different basic forms used in this P language. 2 atomic, 3 form, if form, define form, and the function call form. So function call forms such as time 2a, you will be 2 times 8, and then square root of time 2a, you will have square root of 16, and you got 4. Okay. So in syntax column of this table, symbol must be simple, number must be integer or floating point number, and the other italic words can be any expression. Okay. And the notation of argument means 0 or more arguments. So a language interpreter has 2 parts, parsing and execution. So parsing here is actually including the tokenization. So tokenization means must be done, and then you do parsing. So the parsing component take input program in the form of a sequence of characters. So this portion actually based on syntactic rule, and it will actually do the lexing first and then do parsing. But here we combine them together because scheme is easier in the whole language interpretation. In a simpler interpreter, the internal representation is a tree structure that closely mirrors the nested structure of the statement and expression in the program. In a language translator called a compiler, there is often a series of internal representation, starting with an abstract syntax tree and processing to a sequence of instructions that can be directly executed by the computer. So basically, here is how the parser will do. And the Lisp parser is implemented with function parse. Okay, so basically, parser is a function name called parse. Execution, the internal representation is then processed according to the semantic rule. So sometimes we call it the action routines. Thereby carrying out a computation, and this execution of function code is called eval function. Okay. So here, let's actually look at it, how the picture for it. Okay, so the program being passed become an abstract syntax tree and then being evaluated and get a result. So what a language interpret do? Okay, so here we may have a program. So program equals begin define R10 and then times pi times R. So here we actually pass it into a list or list. Okay, so that list or list we call it program. From string to list or list. And then we have an evaluate function that will evaluate through the pass result of this program. Okay, so simple actually in our scheme language is actually Python's string. Number will be integer or float. So when they are 2 different types, we use multiple tuple. So it can be choose when you try to use type. Atom can be simple or number. So these 2 combined are atom. This is just a list type in Python. So expression can be atom or list. Expression can be atom or list. And environment is a dictionary. So these are the different non-terminal type or terminal type for the scheme language. So parsing, parse, tokenization, and read from token. So parsing traditionally separated into a lexical analyzer and the parser. Okay, so this portion we talk about many times. The Lisp token are parentheses, symbols, and numbers, so it's a list format. There are many tools for lexical analysis, but for now we will use a simple tool, Python's string split function. So that tokenization is can be easily done. So here there is a tokenizer function. So you got a string, and then you replace the so-called single parenthesis with the space parentheses per space. Okay, right side is the same. And you will have your program tokenized. You have your program tokenized, and your program will be tokenized and then replaced and then be split into list. Okay, and this can be done recursively. Okay, so your program will be actually tokenized to result, and your bytes be a list of the tokens that is. Okay, and our function parse take the string representation of a program as input and tokenize them into a list of tokens, then call read from tokens. Okay, so let's look at this one. So here it does has the tokenized tokenized program here. Okay, so this one you can simply run it. Okay, so you get the tokenization result. Now this one you will have this one called parsing. So this one parsing actually is you have the non-terminals. Okay, terminal non-terminals. You have tokenization. You have parsing. You have read from token. So read from token, you will convert from a list of tokens into expressions. Okay, expression is tableable, and atom will be converted from string, a token string, into an atom. So let's look at atom first. Atom is a single element. So you got actually got that. You will try to evaluate if it's integer. If it's integer, we return a number integer. Okay, that's actually atom type. And then if not, we try to evaluate it into float. If not, it will be creating a symbol for it, simple token for it. So either integer or float or symbol. These are the atom type. So the atom type is symbol or number. Number is actually integer or float. So that's atom type. After that, actually, well, you actually have atom. Otherwise, you will be expression. So you read from token, you get everything from the list, and then if a token length is 0, you will actually say it's empty. So you pop you pop the 0 over there. Okay. Otherwise, if the left parenthesis, we will create a new label of the list. Okay. If the next one, okay, if the text, the next one, if the current token is this, okay, we pop the first token. If token is this, okay, then we actually will create this. And if the next one is not this, okay, then we'll append recursively a read from token from there. So basically, this one saying that you have a list. So you have A, B, and then bracket C and D, something like this. Okay, so this one you will actually, if it's a atom, you will actually return atom. Okay, if you see a bracket, you create a new level of bracket. Okay, otherwise what? You will continue to look into the bracket. Okay, if you see another bracket, you break into the next level to create another one. Okay. And when you finish, okay, you append the rest into that, okay. And L is a list. So here, if you pop out, that will finish a label of the list. You go back, okay. And then this one actually, okay. So if the next one actually what you have a current token, you get out, right? Get a token out. And if you actually you keep doing that until you see the right parenthesis. If you directly see a right side parenthesis, then it's error. If it's just a token, you just return the token. So tokenization of the token and the list will be done by atom and this one. Okay, and both of them are actually expression. So this read from token is evaluation of the atom and list, and atom will be specialized treated in here. Okay, and then our top-level parsing is to pass your tokenize your program and send the list of the token into your read from the token. So read from the token actually is your top level recursive evaluation of the expression. So that will pass it. So let's look at the passing result. So passing result will convert this string of parentheses into a list. So here, let's just run it. So it's simply converting the string into a list of the lists. Okay, so that's passing. So passing and tokenization are very simple in Lisp language. So as you can see right here, the parser and the tokenizer we introduced in this lecture are basically using the EHA algorithm. We are using the EHA algorithm to process it. Okay. So token is to talk to tokenization. Passing is converting your expression into a list. Read from token actually is to convert a list or atom into a list. So these are the purpose of that, and we finish that. So next one is environment. Okay, you have a passing, so you build everything into list. Okay, you build everything into Python list from list piece list, from schemes list into Python's list. Okay, so next step we will look into the environment. Environment actually keep track of the variables, keep track of the function call labels, keep track of the temporal value. So an environment is a mapping from variable name to their value. So it's a simple, you can think about it as a simple table, okay? By default, the eval function use the global environment, including the name or a bunch of standard functions. The environment can be augmented with user-defined variables and expressions. So here the environment, you actually create environmental object, okay, and then update variable of the mass. Okay, these are different function. Okay, so you have the different variables. So you actually update it, and then you update the plus sign, minus sign, and then actually star, and then slash. So let's look at the environment type. Okay. So environment type actually, eventually you will actually return environment type, okay? So this one is what? It actually is a, so environment type, let's actually look at it. Environment type is defined in our non-terminals. So environment actually is dictionary. So basically your environment is a dictionary. So your dictionary, basically your env actually is a dictionary. So you actually what? Update your variable mass and function, okay? So this from mass module, you update those functions, okay? And then your plus sign with the operand add. Minus sign would be operand subtraction. Okay, so these are the basic abstraction. And the APS, okay, so these are actually defining each basic functions, okay, and its function body, okay, its function body. So the same thing here. And the env actually is a binding for the environment. So env is a dictionary, it's a binding for environment. So you actually have the standard environment. So standard environment actually will return a dictionary called env type. Okay. So our Lisp programming language actually has what? Has string, integer, float, and then atom list environment expression. And finally, environment is the collection of the total binding of a variable to name or function to name to value. Okay. Variable to value or function to value. Okay, with that actually we have a eval function. Eval function will eval the 5 different forms. Okay, so eval function, you take the expression and using the environment as we know. Okay, so you are evaluating the expression based on the environment we got. Okay, environment actually is global environment. So you have standard environment. Here we have another one called global environment. We shall see it. Okay, and if actually X is a symbol, then we'll return the simplest value, okay, from the environment. If X is a number, we will actually directly return X. So it's instead of checking whether it's a simple or not. Okay, it's this or that. So if the first data is if, then we will return the test result and then get the true part or get the alternative part. Okay, so we will get actually get that. So okay, we have the first value. Okay, if first value if, okay, then we have a test condition. So we'll do tests against the environment using eval, so that it's that. And then if true, we'll return the true part. True part is this consequences. So this one is true part. Else part is here. Okay, else part is here. So we will return if the test condition is true, we will return the we will actually return the consequences. Okay, and at the very end, we will have we will get the expression. Expression can be this or this. Then we'll further evaluate the true part or else part against the environment. Okay, so that will do that. This one is the so-called if form. The defined form, we put the value or expression into your symbol. Okay, and then functional call form, you will use this one as a function. So this one you will evaluate against the environment. That's a function that will apply to with the argument. Okay, evaluate the argument against the environment. Okay, and you will get the arguments. Okay, and you will call the function. Okay, function is the first element. Okay, so you have plus, you evaluate the plus, that would be the function would be plus, and then apply to your arguments, the rest of the list. Okay, so these are the 5 forms for this language, for this language, this P language, and it's defined in the environment. Okay, so we have the program that is, and then we will pass it, and then we will evaluate it, and we'll get the result. Okay, we'll get a result. So it's tedious to have this, have to enter the eval and then pass many times. So you can create a reprint format. Okay, you can create a reprint format. Then we have the reprint format. You can run the reprint format. Okay, and then each time you have printing, your result will be presented. Okay, result will be the evaluation result from the list. Okay, and then that one is a value you need to convert it from scheme to string. So it's converting to scheme language to string. Okay, so let's see. Okay, you converted the string to string. So let's look at this one. The top level is usually called this calculator. So including this P calculator. So we talk about tokenizer, parser, and environment. So everything put together is this Lisp calculator. Okay, so you have everything in here, and then the program is actually, you will actually run the reprint, and reprint actually will go through the reprint loop. Okay, and evaluate your input string every time. So that's actually run it. No, that's actually use a terminal. Okay, let's try this with variable. So let's do define. Oh, I'm sorry. Actually, I'm very sorry because I'm using the infix notation. I'm sorry for that. Okay, so please do not use the infix notation. Let's try again. So let's get out. Okay, let's get out. Try again. Okay, here that's wrong. Okay, so Python Lisp Lisp calculator. Okay, so you must put in the prefix notation. So +1, 2. Okay, that's okay. And then plus, okay, times 4, 3. Okay. Okay, this one you break. So basically, it has a syntax error. Okay, it has syntax. So let's try one more time. So let's do Python. Okay, this calculator. Because I missed the second operand. Okay, so I should do plus 3, 4, 3. Okay, and 10. Okay, and I should be able to do define A and then 3. Okay. Plus 4 and 8. These are defined. So I try the simple. Okay, I try to define. Let's try actually define. Okay, maximum function. Okay, so this is a maximum function. Let's see. Define here. I have maximum function. Okay, with actually x and y. Okay, and this one would be the if. Okay. Greater than x and y, okay, return x, okay, return y, okay, and that's if one more, okay, something like this. So this one doesn't follow this one does not actually follow the grammar, okay. So let's see, here we have a parameter list, so it doesn't take this one yet, okay. So let's actually try this one. Let's do okay. Let's see. Let's do Python Lisp calculator. Okay. So here let's do actually define. Okay. Okay. You should use define. Okay. Define x y. Okay. Greater x y. Okay. X y. Okay. It says still doesn't follow the grammar. Let me check. Okay. So here up to here. Okay. So this one may not be accepted. Okay. So Python Lisp calculator. Py. Okay. Let's do define. Okay. Let's do b. Okay. Plus 2, 4. Okay. Something like this. Okay. And then plus b 3. Okay. So you can only do a very primitive function. Okay. You can only work on very primitive function. You can try it out for this language. Okay. You can only try very primitive function, so don't try something too hard. Section 3, language 2, Lisp. Now we are going to extend the basic scheme language to the next level. We call it Lisp. So language 2, full Lisp. We will now extend our language with the 3 new forms. The previous design, we only have 5 forms. So here we add the quotation. So quotation will actually do not be evaluated. So it's actually the comma. So comma is when you do quote plus 1, 2, you will actually just treat it as a list, but will not evaluate. That's actually bypass. So here you have a quote. Another one is a set Q. Set Q is to set a variable with a certain value. So set Q is a set symbol with some expression. You will evaluate the value and then associate with the value with the symbol. And then third one is a lambda expression. Lambda expression, you have lambda parameter list and the expression for the value. So these are 3 new forms that we added to the full Lisp. So here we have a Lisp and the long list.py. So let's look at the file. So let's continue to go to the project directory, go to lecture 12, lecture 16, and Here we have Lisp number 2. Let's actually look at this directly. So here we have a program called run this. This one just run the repeat. And this P, it has everything you need for the language. So here, let's look at this one. So previous one, we do have the definition for the symbols, for the non-terminals. So symbol is actually string, list is a list, number is a list of floating point. Then we have pass program, and pass program will pass the tokens from the program. Program is a string, and token will actually convert the string to tokens. And read from tokens, you will actually go through each level of the so-called list and convert it to the parenthesis expression, and then convert it to a list. And atom convert a single token to integer, float, or a symbol. Okay, so now we add a apply function, and that will use a function to run with the argument and keywords. So this one is apply function. Standard environment still be a dictionary for it. So here we have create an environment. An environment was defined as the dictionary. So we know that before. Okay, so here we have many things for the operator, for the binary environment. Right here, we actually add one more thing, is that we actually not using the environment equal dictionary, but we do use the environment to extend the dictionary. So here, dictionary, you will look at the parameter list and then create a environment list. So your standard environment here will be assigned as the global environment. So that you create that, and global environment is available to store them. Okay, so here you just briefly check it. Okay, so you provide a fine. So now you have a repeat function here to execute the loop, and then we had a conversion of the list to string. That we had that, and then we have procedure, new procedure function. Procedure class. Okay, and you have eval function, and then this syntax environment that is treated as global binding, sent to the evaluation, and the global binding right here, because you have a seq operator. So the seq operator, it may have a seq, and the global environment will find the available and then update it with the new value. So that's the seq. Okay, and lambda being added over here. Lambda, it actually will call a procedure. So lambda would take the parameter list and body and environment available to put together into the procedure. So procedure is designed to take the parameter, body, and environment binding together to actually set up the lambda expression. And then these are the two new one. And we also have another one, is that actually there's a quote. Quote, actually you will bypass it. Okay, quote, you will bypass it. Here you have a quote. You will bypass the expression when we are not actually evaluate it. Okay, so this one is a newer version for list. And when you run the repeat function. So here, this one similar to the previous language. So let's look at it. Okay, so here you have the top level that will run the repeat, and then you can run it and then get the equation to run. Okay, so let's try this one now. So here you actually create a new terminal. You say Python and then run underline list.py. Okay, it go into here. So now you have the set exclamation mark. Okay, x equals 3. Okay, let's try this one. Okay, this one actually is set exclamation mark. Let's see. The set exclamation mark. Let's check. Okay, this one is wrong list. Okay, it allows the set with expression. Okay, let's try again. Let's try again. Let's have the Python long list.py. Okay, that actually try +3 4. Let's try this one, and let's try set exclamation mark. Okay, and here let's have an X. Okay, and then here let's actually have +2 4. Okay, this one actually will break. So set exclamation mark is not syntax correctly. So that actually look at it, okay? Exclamation mark, okay? Here you'll find the environment variable, okay? So you need to define first. So let me try again. So let's have the Python, okay, run list, okay, .py, okay? So here let's actually define, okay, x equals 3, okay? Let's do set exclamation mark x with 4, okay, and then plus x and 4. So you need to define first before you actually reset it. Okay, reset it. Okay, this run list is a new version with that extension. So set exclamation mark being evaluated. Now let's actually have the code. Okay, and then list 1, 2, 3. Okay, 1, 2, 3 is a list, but we actually code and don't evaluate. Now let's actually have the define, okay, and then maximum, and maximum define as a lambda expression. Take x and y, okay, and the value is actually do if, okay, and greater than x and y, you return x, otherwise you return y, matching with the parentheses to the if, and then matching the parentheses to the lambda, and then matching the parentheses to the define, and he return. And then let's run maximum, okay, 1 and 2. Okay, we get a maximum for 2. So here we can do control get out of the program. So this one is how our language number 2 will do. We actually add 3 different function, but remember that before you do set Q, you must define it first. Okay, set exclamation mark, you must define the variable first. So this run list language now combine the language 1's 5 form, including a simple, number, conditional, define, and the procedure code. Also, including the newer definition that including the quote, symbol, and lambda, okay? So that's the language number 2, okay? So in the first step, the lambda expression is very well to create a procedure, one which prefer to the global variable pi and star, okay? Take single parameter, which is the radius r, okay? This procedure is used as the value of the new variable circle area, okay? So here is talking about running this example. Okay, second step, the procedure just be defined in the value of the circle area. So it is called with the value obtained as the argument, and we want R to take on the value obtained, but it won't do just set R to 10 in the global environment. What if we were using R for some other purpose? We would want to call a circle area to alter that value. Instead, we want to arrange there's to be a local variable names R that we can set to 10 without worrying about interfering with global variables. Okay, the process is for calling procedure introduce these new local variables. So that's a new environment we'd like to bind to. Okay, so we define the env that actually is dictionary as a class, so we can use many times. So we use our default env as a global definition, and we also can create local definition use env constructor. So let's look at it. The standard env is actually a global definition. So let's look at it. Look at the code one more time. So env is a class. Env is a class, and we have a standard definition as a function. It will create a env, okay, and the env is a dictionary, okay. It's actually using the env class, and env actually extend dictionary, so it's still a dictionary, and you return it. So this one we actually define the standard env to the global environment. But when you do the function call, you may have its own local env, okay. So you can pass the env to it. Let's say your local env, and you can create a, when you call a function, it will create its own local env to it, okay, including the pass value of a parameter body and env to its own. Env is a dictionary, okay. So you kind of can use the env as a constructor to be your local definition and the global definition when the function is called. So you pass the global env when you actually evaluate, okay. But in some of the evaluation, if, okay, or you have a define, you are actually binding some env to it, okay. So that actually is our language number 2. So we will redefine a env as class, but env is a class, but it will still be a dictionary because it would extend the dictionary. Because it extend the dictionary. So this different parameter will be binding into the local binding. Okay, so the blue one is local binding, the radius is local binding, pi and the star, these are global definitions. So when you run, you are using these 2 reference environment to run it, okay. So that's that. So we have this listing for the env as dictionary, and that actually is env actually extend the dictionary. So, and we define this class so it can be called many times to create some local env as well, okay. So here, this one is the evaluation. When we evaluate it, it may have a local env created in the middle. So here we define env as class. So we have yellow one, so set balance plus balance amount. Okay, so here this one is local label. Okay, and then you have green env, and then blue env, and then red env. Okay, it's different level of the env. So env will be a parameter will be passed to different function. Okay. So each rectangular box represents an environment, so that we call it reference environment, and the color of the box matches the color of the variable that are newly defined in the environment. So that's your reference environment. In the last 2 lines of the program, we define account 1 and the call. These represent a certain the creation of a bank account with $100 opening balance, followed by $20 withdrawal. Okay. In the process of evaluating these, we will evaluate the expression highlighted in yellow. These are 3 variables in the expression, and the amount can be found immediately in the green environment. Okay. So that you search from the global, local. If local doesn't have, you go back to search your blue. If blue you don't get it, you go back to search your red one. That's a global environment. Okay, so that's the rule using the find to find the closest lexical environment. So we already run it, and this one we actually can use this. Okay, we can actually have this lambda, okay, this lambda, and this different lambda we actually can put into there. We can put it line by line to my list. So you can open down the scheme language file and then copy line by line to fit into your this.py program. Okay, you can fit into there. So we now have a language with procedure variable conditionals. So you have function call, you have if, Okay, it's similar to you have structural programming environment. You also can set variable. If you are familiar with other language, you might think that single while or for loop would needed, but scheme language to do without these just fine. Okay, we actually have the recursion to work as for in the place of the for loop. The scheme report say scheme demonstrate that a very small number of rules for forming expression with no restriction on how they are composed suffice to form a practical and efficient programming language. Okay, in scheme you iterate by defining recursive functions. So here we do have basic one. So in the language 2, we add the function called if statement for conditional statement. So it and also set available. These are 3 important things when you work on the structural programming. Okay, 3 things that are very important to the structural programming. And we are going to the next one, the language 3, that will be adding some new data type. Section 4, language 3, advanced Lisp. So now we are going to introduce the most advanced Lisp languages for scheme, part 1, new data type. So we actually add more data type and more feature to it. First one, we allow string, Boolean, and complex and port. Okay, so string, it actually has string data row. So you actually can be enclosed by double quote. Okay, that actually is a string. Within a string, you have \n for new line mark. Okay, this we know from different language. Boolean value, you have sharp T for true, sharp T F for false. Okay. So, and we also allow the complex numbers. Complex number, you can write it in 3 plus 4i. Okay. Port, it actually allow the different port. You can get it from file, get it from keyboard, get it from different places for port. And we actually update the symbol. So symbol, it used to be just a string. So right here, we actually create a new version. So symbol were implemented as string before. Now we have string. Symbol will be implemented as a separate class. So it derived from string, and it means that it no longer can be written. We no longer can read that actually if x of 0, okay, equals if, because if is now a string, not a symbol. Instead of this, we write x0 as underline if, and define underline if as a symbol of the if. Okay, so when symbol, so this one it becomes a string, and this one actually is a symbol of the if. Okay, where symbol manages symbol table. Okay, of the unique tables. So okay, so there is a symbol. So here symbol, you maintain a symbol table now. It used to include every string, but now it actually symbol is actually including the string. Okay, so sim is a symbol table. Okay, so this one we actually put the keywords and different sim in the sim as the table. Okay, so we have that, we create empty that, and then we loaded the different ones. So we have a quote, if, set, define, these different keywords putting into my sim table. And the second one, new syntax. Okay, so this one actually we allow the string and Boolean. Now we actually have new syntax. So in addition to string complicated tokenization, no longer can space separate deliver token. Okay, so sometimes space cannot deliver the token. So we actually will because the space can appear inside the string. So instead, we use a complex expression to break it down. Okay, so we will use a regular expression to allow it. Okay, so token sharp T sharp F are the true and false literals. Okay, and we actually allow it. In the previous version of this, all input are read from string. In this version, we start to introduce a poll, keypole poll, and also the file poll. Okay, so you make the read evaluate print loop, okay, more convenient. So this one you actually make it more convenient. in that way. And we have import. Import, actually, you have tokenizer that allow the different token, okay? And you have the file. You actually open the file, and then you try to get every token from the port, and you start to evaluate it, okay? So this one, you redefine the import class, and your next token being created. So import is a port that you get data from keyboard or file. So now you also allow the string comment and call and literal into the language. So you actually allow them and implement them there. And then you can load, and you have a repeat function, okay? And then you also allow macro. So macro is a definition that you can use in-text, inline replacement. So macro definition are only allowed at the top level of a file or iterative session, okay? And so you also start to allow that function, okay? And macro table, you have a lot. And then we actually also optimize for tail recursion optimization, okay? So scheme has no while or for loop, relying on the recursion for iteration. This makes the language simple, but there is a potential problem if every recursion call grow the runtime stack, then the depth of the recursion and hence the ability to the loop will be limited. In some implementation, the limit will be as small as a few hundred iterations, then you may have stack overflow pretty soon. This limitation can be relieved by altering eval so that it does not grow the stack on all recursive calls. So try to optimize the tail recursion. So try to optimize it, okay? Try to optimize it. Consider the re-evaluation of this thing, okay? When v equals 1 and twice is the procedure of this, okay? So your twice that would do multiply of it, okay? So you have a tail recursion, tail recursion, tail recursion, tail recursion. So basically, being passed back until you do final evaluation, okay? So that's called tail recursion. You can optimize it. So here we redefine the evaluate function to allow it, okay? Procedure, we are here. And then, okay, you can design some sum2 function for scheme language, okay? And you can run it, use your Lisp. So here you can copy the file into it, okay? And you get it. So let's try this one, okay? Let's try this one. So this version, actually, you do not need to use it for different, you don't need to use it for you don't need to use it for line by line, okay? You can do Lisp.py, okay? So right here, it see the mark, okay? And right here, you copy the whole define, and then you pass here, and then hit return, okay? And you get this different value. So here you have the sum2 and the sum2 version. So here that's actually wrong, sum-2, okay, and then 10, and then you get 55. Okay, so here that's wrong, sum-2, okay, and then 40. Get this, okay, and we do control it to get out of the Lisp evaluation. So this is how it works, okay? So this version, as you can see, it does support you to have multiple line evaluation, okay? So this one, the Lisp is more advanced. It is more advanced, okay? It allows the multiple line execution, okay? And so we have the several good features with this version. It's more complicated, okay? And then the next one, code with current continuation, okay? So it actually do not need to actually have single line for it. So we have a code with current continuation. Okay. So here you can put a whole function to that. So you do not need to write the function in a single line. Now you can allow multiple lines for it. Okay. So this one actually is pretty convenient. Okay. So let's actually run it one more time. Okay. Run it one more time. So let's do, here we have the Lisp that Python that this, okay, Python and then Lisp.py. Okay. So right here that actually do have define, okay, define, and then we have maximum, okay. So here let me actually change it for the second line. So here let me save some space and I say lambda. Okay, here I have x and y. Okay, so here with this one I'm going to provide value. So here I'm going to have -1. I put my if, okay, and then greater than x and y, okay. Here I'm going to return x, okay, and then I return y if alternative and parentheses for if, okay. So right here parentheses for lambda, okay, right here parentheses for define, okay, and right here I start a new one. I say max of 3 and 5 and hit return, so I get 5. Okay, so here as you can see, this one more efficient when you try to match the parentheses. You can have the kind of some sort of editor that you can edit your program. Okay, so that's the advantage of this program. You got the code with current continuation. Okay. They can continue with that environment to continue to code. Okay. Okay, so that's another feature. So next one, number 6, procedure with arbitrary number of arguments. And this one, we can have list and more number. Okay, so you have the list function. So this one, you can use the argument list, okay, star argument that we teach you in the object programming, object-oriented programming for Python, we teach you already. So this one you get argument, okay, and using the argument list to create the parameters, okay, parameters. So that would be arbitrary long of the arguments. Okay, and we have the early error detection and extended syntax. And we have this different, so consider this different error code. In the first version of Lisp, evaluation this definition will not yield any complaint. And in fact, it just breaks the program, okay? If you are wrong, it will program. But as soon as any of the function will call, runtime error will occur and we will break the program. In general, errors should be reported as early as possible, okay? So let's see, this one we actually, this version will report the error, okay? So we have a different one, okay? These are extended syntax, okay? And we will report the past error, okay? And okay, we have expand function, okay? Let's look at the error. So here, let's see. If we run it, okay, let's run it. Let's run Python, okay, Lisp p.py. Okay, so here let's assume that we have actually A. I'm sorry, I have A and then 1 and 3. A is undefined, so let's do this one. I will get a lookup error A. Okay, I'll get a. In the previous version, I do not have the report of error, but here I do get it. Okay, in this version, I do get the report for error. Okay, so that's it's another good advantage of it. You get earlier detection of the error. Okay, you have expand function. Okay, expand function will go through the code. Next one, we have more primitive procedures. So primitive procedure is very important because most of the time we are calling the built-in functions to perform some operation, okay, to perform some operation. So here we actually have the pair const function, okay. We do have more global, so here more function being added, okay, being added, more function being added in here, okay. And we can do testing. So testing is very complicated. So we create many .scm file. Okay, you can copy one by one to the environment. So here we do get started to test it, and when we copy the test one to over here, and you test, and the test scheme language 2, we proceed, you will test it, and then 3, 4, 5, 6, 7, 8, 9, 10. So we try to use many scheme language to test our environment. So right here, you can see we have the different test.scm, and you can copy them to the environment to test. Okay, so for that test, I pretty much do is Python Lisp py, okay, over here, and I open my test number 1. So here, test number 1, I am going to actually copy the whole thing, okay, copy, and then paste over here. So you run all of the different instructions that defined in this test1.scheme language file, okay. So I kind of testing the different program. Section 14, conclusion. Programming language course. We have finished a very interesting course. This programming language course is actually targeted at the study of the programming paradigm, the design of the language, and the implementation of the implementation of computer programs such as interpreter or compiler design. So basically, programming language is a course to design and implement your language and use that to solve your computer science problem. In this course, we use Python language as our core pilot language to study the programming language features and programming paradigms and lectures and parser and tree evaluation, and also virtual machine, and also the interpreter design. So Python as a language is very versatile, so it helps us to study these different topics. We have tried to have different analyzer, ad hoc lexical analyzer, and use LEC pre to do lexical analyzer parser design. And we also present a recursive descent parser design, and also talking about the virtual machine, and also finally the ad hoc version of the scheme interpreter design. And programming language pragmatics is to study the structure and interpretation of the programs. And it is very useful software. It can be used to compiler design, interpreter design, web engine design, natural language processing design, and also conversion of the markup language to graphical conversion, or rendering your graphic in your web page. So it's very powerful and very useful. And in this course, we try to provide a fundamental knowledge for the design of interpreters. In the real world application, the interpreter can be much faster and actually can have more, can be much faster and also can be more complicated. There should be a lot of different engineering issues that we did not cover in this course. So enjoy the use of these tools, and enjoy to design your own programming language sometime in the future. Okay, thank you. This is the end of the chapter 10C, and also the end of the course programming language. Thank you. Bye now.